Hello, my name is Dylan Radulski. This is Physics 2211, Lab 1, Constant Velocity. The purpose of the lab was to analyze the motion graphs and data of the movement of an object in the lab. The object had to be moving at a constant velocity. The fundamental physical principles were the position update formula and the velocity update formula. However, the velocity update formula would end up just equaling velocity final equals velocity initial since forces were zero and constant since the object was moving at a constant velocity. The results of the lab show us that due to the zero net force acting on the object pushed, velocity remains constant, which results in a linear, positively sloped position versus time graph. These graphs were provided by the program model, not the physical test. The lab setup. For this lab, we used a provided cart and track in order to get as close as possible to constant velocity as possible in the real world. The wheels on the cart made it so that way there was as little frictional force in play as possible, and we had the cart going at a fast velocity in order to minimize the effect of said friction on the cart over the short 1 meter distance. We used a meter stick to set up the measurable distance for the tracker application and analyzed the motion of the cart using the tracker application to provide data for the lab. The system for the video, the system is the cart and the surroundings are me giving the initial push, that is before time equals 0, the track, and earth. Here's the data. You can see the time and the position. The numbers divided by the tracker application are sorted onto an Excel spreadsheet, and the time and position of the cart are listed to the right. These numbers were used in order to calculate the initial velocity of the cart using a simple displacement over time formula. This equation equaled to an instantaneous velocity of 1.2 meters per second, which was used in the prediction model to predict the movement of the object. The initial position of the object is just slightly behind the origin on the x-axis due to slightly inaccurate measurements using the tracker application, but in the computational model, which will be shown later, the initial position used was 0, 0, 0 meters, the vector. The important code. The ball started at 0 meters, and I set its initial velocity to 1.2 as calculated before. The time obviously starts at 0, and the delta t is equal to 0.032 seconds, which is provided by the tracker application and determined by the frame rate of my video. The while loop ends at the same length as the length of our video in order to get roughly the same distance traveled, and f net is equal to 0 since constant velocity is what we're trying to measure. The rest of the code is just the velocity update formula, which is always just Vf equals Vi due to constant velocity, and the position update formula, which uses the velocity and delta t to calculate a new position at each step. Here's the data from the code and the tracker. It is compared with the blue line is the position of the real life example, and the simulated is the orange line. You can see that the position of the real one is more slanted upward, which means that the velocity would be calculated and used in the simulation was just slightly under the real velocity of the object, but both lines are relatively straight and both show a constant velocity. Possible sources of our error was misuse of the tracker application, false assumptions regarding the friction on the cart, and improper use of the improper velocity when coding. What if we flip the axis in the tracker application? The velocity would remain the same, just in an opposite direction. The only difference would be the direction of the slope in the position graph and the sign of the velocity graph. The new position versus time graph would be downward sloping, and the velocity versus time graph would be negative but have the same magnitude. What does it mean? Is it possible to name all the forces acting on the chart that resulted in an f net of 0? I can certainly try. One is gravity, normal force, friction, my initial push, which was before delta t, but still, before t I mean, and wind resistance. I'm sure that there are more forces acting on the system that I'm too ignorant to list.